Hello and welcome to this video on unifying constraints with typing rules in the Hindley-Milner type system. This is part of a subseries to do with Hindley-Milner typing rules, which is part of a wider series on Hindley-Milner. If you haven't seen the previous videos, go and have a look at those. In those previous videos, we looked a bit at typing proofs. So this is an example of a typing proof, either set out as a type proof tree at the top, or as a list of statements as in the bottom. Both of these are equivalent. We built this up making some assumptions about what rules we could apply, how we could apply them, how we could substitute different types in, basically because we knew what the result was going to be at the end, really. We were just saying, well, this rule has to fit in here, or we were kind of assuming what we were going to take out of the context, etc. What if you didn't know those rules? What if you were a compiler without that kind of common sense or common understanding of an obvious goal we were getting to? How might you do that? So in this case, we want to ask, what's the type of odd age? But then we don't know anything really else about it, right? It's just something. So let's start by just giving this a variable. We don't know what it's going to be. It's going to be some type variable, and we're going to say that type variable is going to be t0. So it's going to be some type. We don't know what it is yet. We'll just call it t0. But what we can say is this is a function application. We know that. So it's going to have some function application parts to it as well. So there's the odd, the expression 1, and age, expression 2. What are the types of these? Well, we don't know the types of these either, so we're just going to leave them as question marks. Well, we need to assign some kind of type to them. So how about we say, let's make up some new type variables. So odd has to be a function, that's by the rule. So we'll say that's t1 to t2, and age has to be some kind of thing that goes into odd. An argument will give that a type t3. We'll just say that's t3. All of these are just new variables, but we do know that there are some relationships between these. So for example, our rule, if we look at how that linked up on the application rule, you can go back and have a look, specifies that, well, age is the argument of odd. So that t1, the kind of from type of odd, has to match with the kind of type of age. So we should say t1 should kind of match with t3. And the return type, the t2, is going to be the type of the overall expression. So that's going to match with t0. So underneath, we've put down these constraints. So we're going to say t0 should unify with t2, and t1 should unify with t3. So let's carry on. What else can we say? Well, if we look at our two expressions, we've got from the context gamma, it follows that odd has some type, and also that age has some type. Well, odd and age are both just variable expressions, so we need the var rule. Let's try the var rule on odd. Again, we're not sure what exact assignment we should be pulling out of the context. We just know it involves the expression odd. So that's got some type going for it. Again, we'll create a new type variable for that. We'll say that is t4. And similarly, as we did with the function application, we can say, well, the type of odd, we said in the top left of the application rule that the type of odd was t1 to t4. And in the var rule, the way those two correspond is that the bottom type should be the same as the top type. So that's t1 to t2 should unify with t4, right? So you can say t1 to t2 should unify with t4. There is another thing we can do though, is that we know odd has type t4 in gamma. And if we look at what was in gamma in the context, well, we saw that odd has type int to bool. So we actually know this t4, the only option for that to be in the context is t4 has to unify with int to bool. So we can also say that t4 should unify with int to bool. And at that point, we're just looking inside the context. We say, well, odd has some type in the context. We can just look through all the statements in the context, find the ones with odd on the left-hand side, and take the type on the right-hand side, say that must unify with the type variable t4. Okay. And moving on to the right-hand side, we've got from the context gamma, it follows that age is type t3. We can do the same thing where we have a var rule here. We can say, well, age has this new type t5. If we look in the context, t5 should unify with int. And also based on the var rule, well, t5 should unify with t3. Okay, so we've completed our type tree, but we haven't actually put any types on it in terms of what is t0. And we still don't really say t0 is unifying with anything yet. So let's get rid of the rest of the tree. We just need this part. From the context gamma, it follows that odd age has type t0. Again, we don't really know what this type T0 is, but we know it has to satisfy these constraints. So for example, that T0 has to unify with T2, T1 has to unify with T3, T1 to T2 has to unify with T4, T4 has to unify with int to bool, T3 has to unify with T5, and T5 has to unify with int. So let's try actually unifying these pairs. So let's start with the first of them. T0 should unify with T2. And if it should unify, well, when we call the unify function on this pair, we should get some substitution which we can apply to the rest of our expressions that will help unify these two together. So let's try that. What happens when we unify T0 and T2? One possible answer is we could get the substitution T0 maps to T2. Again, go back and watch the videos on substitutions and unification if it's unclear how we're doing this unification process. If you're unclear why we're doing this unification process, that's because these two types have to basically be the same type. And so we want to figure out what are the structural similarities that we can match there, what kind of substitutions can we generate to run these mappings across everything else to help simplify and combine these constraints as we go through. So let's try applying the substitution everywhere else. Well, let's have a look. It maps our T0 to T2. The only place where we have a T0 is actually in the kind of question we're trying to answer. So let's map that to T2. But there are no other places that T0 appears. So we're done applying the substitution. We've dealt with this constraint. Now we can move on to the next one. So let's look at the next one. In this case, we're unifying T1 and T3. We get the substitution T1 maps to T3. And then we can see, well, there's one T1 here. We can map that to T3, and then we're done unifying those two. Let's look at the next one. In this case, we're unifying T3 to T2, should unify with T4. And what can we get? Well, we can get that T4 should map to T3 to T2. So let's try applying that substitution everywhere. Well, we see there's a T4 over here, and we can update that to T3 to T2, should unify with int to bool. That's fine. So actually, let's do that one next. We should be able to unify these two things. We should unify T3 to T2, unifies with int to bool. And again, this is exactly where the unification process comes in handy, in that we retain the structure of that function type, but we still have the mappings inside. So we've got a mapping of T3 to int and T2 to bool. So let's try those. Well, T3 to int, we'll update that T3 there to an int. And we can also see there's no other T3s. So let's move on to the other part of the substitution. T2 maps to bool. We've actually got a T2 in our original expression. We can update that. And then, to be honest, we're kind of done, right? We've figured out that odd age has type bool, and that is the right answer. That is exactly how you could find it out if you were doing this, without any kind of specific goal in mind. You were just applying the rules, and you wanted some process for finding the type. Although we're not quite done, because we haven't finished off all our constraints. And so, although at this time, based on our constraints so far, we think odd age has type bool, what could happen is that another constraint now actually doesn't work, and that means there's some type error. That means the whole expression is invalid, and actually what we've derived so far might actually be incompatible with some other part of our expression. So let's keep going. Let's take the next one, unifying int and T5, and we map T5 to int. We'll update that where we have the T5. And then finally, let's unify these two. Well, we unify int and int. In fact, these are identical, so there's just an empty substitution unifies these. We don't need to apply any mappings, and there we get kind of the same expression. And we're done. We've dealt with all of our constraints. We found the type. Odd age has type bool. And actually, if we go back to our original tree, so this is what we had after we went through and derived all those different new type variables and the constraints. If we had applied all those unifying substitutions to the whole tree, you'd actually see we'd get the type at every point. So you'd end up with this tree, which is also the same tree that we started with at the beginning. If you want to, maybe it'd be a good exercise to pause, go through and just try that for yourself, or try it on another example, and see how those typing constraints can be kind of combined through that process of continued unification and then applying those substitutions, and see if you can get a nice type tree like this. Thanks for watching. In the next video, we'll look at what happens when you do get a type error and how that surfaces.